Thanks, Aditya. Can you see my screen?
Yep, it's clear now. Yep.
Thank you. And can you still see it now?
Yep, I can see it. Yeah. Yep.
Okay, thank you. Thanks very much. Thanks for the kind introduction. My name's Ian de Klerk. I'm an executive consultant with Snowden, and I'll be giving you a quick overview of Snowden's software offering called Supervisor, and we'll be looking at particularly variography and conditional simulation on a cold data set. I think Aditya has covered all of this. This is just by way of a small introduction. So let's get straight into it. This is a brief outline of what we'll be talking about. We'll be doing a very high level review of Supervisor. Supervisor contains a lot of functionality, and we'll really only be touching on the bits that are relevant to the presentation today. So we'll have a look at loading data, viewing data, and the associated histograms. We'll move on to have a look at constructing semivariograms, and Supervisor is well known in this field. We can also have a look at conditional simulation on a cold data set, and then we'll interpret some of the results from the simulation. So the project tree window that you'll see on a Supervisor screen on the left-hand side, this is it here. This is your project tree. And this is, it's very versatile. You can load your data and group it by assay under domain or domain under assay. Here you can see the assay is loaded, and underneath it are the domains. In this case, there's only one domain called domain 100. Down here, we have the domain loaded as the primary grouping, and underneath it, we have the qualities, the assay parameters loaded. And this is quite useful. It's very flexible and easy to change this tree, just simply both drag and drop. And you can have unlimited groups here. You can insert various functionalities. So we'll be looking at variography and conditional simulation in particular. And you can alter or change these groups and move them around without affecting the other components. And you can also save templates when you're happy with the structure of your project tree. You can save templates for future work. Just some of the quick overview of the data analysis functionality. Supervisor produces at the click of a button, really, histograms, log probability plots, mean and variance plots. These are useful if you're doing top cutting. These are scatter plots where we can look at correlation between different data sets, box and whisker plots, and this is a QQ plot. So it's very easy to analyze your data, really just a couple of clicks of the mouse once your data is loaded. We'll be focusing today on variography, and Supervisor really is, I think, a world leader in this. It's the simplest software I've ever come across for developing variograms. So it'll deliver to you a set of continuity fans where it's easy to develop your main directions of continuity, to develop the axes of your search ellipsoid and the orientation of your search ellipsoids. The variography itself, it plots automatically the experimental variogram, and then really the modeling process consists of dragging toggle bars around. It's all interactive, graphically interactive, and very intuitive. So we can just drag the bar here for changing the lag distance, and we can move these toggles around to set the range and adjust the range for modeling of your variogram. It will work with data in transformed space and automatically back transform the data when you're ready to go. And it will also export the results of the variogram analysis to various, to many modeling software types. They're all listed there. It's just a drop-down list. You choose what you're using, whether it's Vulkan or Datamine, etc. And it will output your variography data in the correct rotation. One of the other key functionalities is the ability to produce a conditional simulation. This is very easy. Here we use sequential Gaussian conditional simulation. And here's some pictures of output from a simulation, particularly probability type outputs, grade tonnage curves, and also QQ plots, where we compare the simulation result with the actual data. So loading data in is really very simple. You load from a CSV file, and here is a summary view of the cold data set that I've loaded. So there's 1,782 drill holes loaded with their coordinates. There's information loaded into 3 different domains. And here are the variables we've loaded. We've loaded the coal seam thickness, the relative density, the raw ash, the raw calorific value, and the raw sulfur. So I'm going to proceed with a series of videos that will take you through the aspects that we've just described in overview form so far. So let's have a look at viewing data and histograms in Supervisor. Now that we have the data loaded, we can start to view and analyze our data. Let's begin with 3D Viewer. So here we can see our data points color-coded according to domain. So the blue colors, the blue area is domain 100, the central green area is domain 200, and domain 300 is the red area. If we change this to look at the raw ash values, which will be a theme throughout this demonstration, we can see the raw ashes color-coded according to the legend on the right. And we can see immediately the rationale behind the definition of domains based on ash content, where you can see the central area with ash contents more or less in the central range of the domain. Probably of more useful is to color code the ash data, ash content, according to deciles. So we're showing now each decile percentile of the ash content distribution, so that we can see here that the dark blue area in this area here is the first 10% of your ash content distribution. So these are the very low values, and the red areas, or the red squares, denote high ash contents towards the 80 to 90 and 90 to 100% end of the ash content distribution. Again, this shows quite clearly the domains that have been defined, and it also illustrates that some subdomaining may be required here, particularly in this area here of domain 100. We see a region of high values, and in this northern part of domain 300 we see a wide range in data values, and also some fairly sparse drilling data. So it may be an idea to subdivide this domain. We can also restrict our viewing and analysis to particular domains. So if I click domain 100, then we only see the data present in domain 100, and similarly for domain 200 and domain 300. When we loaded the data, certain statistical analyses were inserted automatically into the project tree. So let's have a look at the histogram. And this is the histogram for domain 200. And we can see that within that domain, 814 samples are present out of a total of 1782. Various statistical information is given down the side here, and you can use this box here to customize exactly what you'd like to see. We can also color these histograms, and there are numerous options. Typically, if you wanted a 95% confidence interval, you would choose that, and the green would be 95% of your distribution, about the mean. You can also useful is to color code it by deciles. So here we see the 10% deciles throughout the distribution. That can be very useful. We can look at it as a log transform data. Obviously not useful in this case, but the facility is there. And we can overlay the cumulative distribution frequency or change it to the actual cumulative histogram. And the histograms for the relevant coal qualities can be accessed just simply by clicking on them. So that's the raw calorific value, that is the relative density, that is the sulfur, and the seam thickness. Now that we have the data loaded, we can start to view and analyze our data. Let's begin with the 3D viewer. So here we can see our data point. Sorry, I started that again. So if we move on to the variography element, I'll play another video that that illustrates creating variograms in Supervisor. Let's have a look now at developing semivariograms in Supervisor. And we're going to look at the variography of raw ash within domain 200. So if we select raw ash and add a horizontal continuity fan, and we update this by clicking on the green arrow, this creates a circular 360-degree map showing contours of the variogram variance in directions around the 360-degree view. If we increase the lag separation by simply dragging the bar to increasing lag distances, we can see these contours start to open up. We can also increase the resolution of the fan by changing the number of rays from 18 to 30, let's say 36, and we'll have to update the fan. We can also change the distance the fan is looking away from the central point by changing the separation distance, let's say to 4,000, and we'll rerun it. We can now toggle up and down the sideband here to zoom in and out on our variogram variability map contour plan. Let's reset that to 2000. You'll notice that the variance contours on the fan have been color coded according to their variability. So the blue color is from 0 to 0.7, the lowest variability, and then green is 0.7 to 0.85, and red is from 0.85 to 1. 1 represents the variogram sill height, and these variograms have all been standardized. This means that all gamma values from the variogram have been divided by the sample variance, and therefore the variograms obtained on the right-hand side here are all directly comparable with each other. These variograms have been generated to represent each ray around the 360 degrees of the fan. The pink-colored variogram up here represents the direction of the continuity arrow on the fan. This fan, this continuity arrow can be moved around the fan, and the idea is to indicate the direction of maximum continuity. As we move it, we'll notice that different variograms are highlighted according to the direction of this arrow. The variogram fan is a very informative method of determining whether the deposit or the particular parameter you're looking at is isotropic or anisotropic, and if anisotropic, to determine the direction of the major axis of longest continuity. Something to note is probably that many coal deposits that are simply assumed to be isotropic on analysis like this turn out to be clearly anisotropic in nature. So when trying to determine the direction of maximum continuity, all of your knowledge about the deposit should come into play. But if we look at this variogram fan, we're going to conclude in this example that our maximum direction is towards 345 degrees, as indicated by the green, the preferred direction of the green contour lines. And since our coal deposit is effectively two-dimensional, and we are looking at the horizontal continuity fan in the horizontal plane, then we assume 345 degrees represents direction 1, our direction of maximum continuity, and our direction 2, or what would represent the semi-major axis of the search ellipsoid, will be at 90 degrees to direction 1. A couple of quick points here. If we wanted, for example, to view one of these variograms in a particular direction in a bit more detail, we can just simply double-click on it, and it pops it up in an exploded view here. And we can change the lag distance and view that in more detail. Notice that the fan changes interactively at the same time. If we want to return to the previous view, we simply double-click in the top right-hand corner. Also, if we would like to treat our deposit as isotropic, in other words, no preferred direction of continuity and an equal search distance around the ellipsoid, we can do that by changing the angular tolerance to 90, in which case it's going to search all the way around in 360 degrees. And you'll notice now that our search is isotropic, and we will be developing omnidirectional variograms from this. Now that we've determined our major and semi-major directions, we can proceed with variogram modeling. And we will add continuity models under our horizontal continuity analysis. This automatically inserts continuity models, and we will now proceed with modeling the variography. And we're presented with 4 cases to model. The first being the downhole variogram, which is not applicable in our case since this coal deposit is 2D in nature. This is our direction 1 towards 345 degrees. This is our principal direction of maximum continuity. So we will develop the variography for this. We will also develop variography for the semi-major axis direction, which is 90 degrees to the principal direction. And then direction 3, which is effectively the plunge direction, is once again not applicable in this case. So really we only need to concentrate on the variography for our principal direction and the direction perpendicular to that. Let's begin with direction 1, our direction of maximum continuity. So once again, if we double click on this, we can expand it. We open up the lag spacing in an attempt to find an appropriate lag spacing in order to model the lag spacing with a suitable experimental variogram where we can start to model the blue bars here represent the number of pairs that we use to generate each experimental point on the variogram. We also notice that there are few points at a short lag spacing, and also the first point here is fairly high on the gamma scale, representing quite a high variability. The reason for this is if we go back to our 3D viewer and look at domain 2, you can see there are ash content values in here where we have high values and low values close together. And this is what's causing the high initial gamma values. Next, we're going to set the transform to a normal scores transform. The reason for this is that in the subsequent conditional simulation exercise, we're going to need to use variograms from our that have been developed in Gaussian space. Also, we're going to open up the total separation here to about 5,000 meters so that we can look further out. If we go to the Model tab, we can click the Auto Fit button and just see what we get. We can choose different model types here. In this case, the default is spherical. In this case, it's used two spherical models to model the data. We could try adding a third to see if that would improve the fit at all. We can move these points around just simply by clicking on them and dragging. This is a very useful and intuitive way of modeling variograms. So we can change the nugget effect, and we have a toggle for each of the spherical models it's employed, and we can simply drag and drop these to model as best we can the experimental variogram. It's really up to the user, and it takes very little practice to be able to employ this to generate quite accurate variogram models. There are a few observations we can make here. At about 1,500 meters, you've reached approximately 0.8 of the total sample variance, and one wouldn't really want to search out further than about 1,500 meters when doing the estimation. Also, you'll notice that the model gradually approaches the sill and then crosses over and continues to rise. This is indicative of there being a slight trend in the data, but not too much concern to us because we will focus down here for our estimation in the sort of sub 1500 meter distance region. If we're happy with this model, we can lock the sills and return to the previous and then model the semi-major axis at 90 degrees to the principal direction. Again, we can adjust the lag distance until we find the optimal spot that we would like to model the experimental variogram. Again, let's open up the maximum separation. And again, we can proceed with modeling the variogram by pulling out and adjusting the toggles for the various models, remembering that the sills have now been fixed. To check the robustness of your model, we can change the lag spacing again and see how the experimental variogram agrees with the model. So we're pretty good really there. You'll notice in this area here, the close space data is not good in this example. But we'll probably set a search radius for the semi-major axis of probably roughly about 1,000 meters, which gives you about 80% of the variance on your variogram. So if we close this tab, we can see now that we've completed the variogram model for direction 1 and for direction 2. We now have our normal scores horizontal continuity model defined for domain 200. And I've gone ahead and done a similar thing for domain 100 and for domain 300. Let's have a look now at developing Semivari. All right, jumping around a bit. Okay, so we've developed our variograms in Gaussian space. In other words, they fit a Gaussian distribution. This is required in order to do the conditional simulation. So let's move on now and have a look at the conditional simulation component. For the last part of the presentation, let's look at setting up a conditional simulation. So in Supervisor, we come up to your main data window and we add conditional simulation. Now, what is a conditional simulation and why do we want to add one? Some of the advantages of doing a conditional simulation are listed in the slide. Conditional simulation reproduces the variability of the data set, unlike traditional estimations such as kriging. With kriging, the assessment of uncertainty depends strongly on the sampling configuration, without any reference being made to the actual magnitude of the grades themselves. Some of the properties of conditional simulations include the simulation honoring the sample data points. They also reproduce the sample histogram, and they'll reproduce the spatial variability of the variable of interest and allows the opportunity to determine the probabilities above cutoff grades. They're also particularly useful for drill hole optimization studies and to assist with resource classification. This small diagram illustrates some of these points. The thick continuous black line represents the actual variability within the deposit. It represents reality, which we don't know. The thin dashed line represents a creaked estimate, where we see estimations at the small open circles where along the reality line. And so we see that the creaked estimate, the continuous dotted line here, does represent reality at the points at which its estimate is made, although overall it results in a very smooth estimation of the variability of the deposit. On the other hand, the thin solid line represents a simulation, and here we can see that the true variability of the deposit has been reproduced by the simulation. So the simulation also provides estimates, as does the kriging, at points of intersection where the estimate has been made, and these estimates will honour the known sample points. But the overall simulation does represent the true variability and histogram of the known sample points. We set up the conditional simulation parameters on the right-hand side here, and I won't run through all of them, but in this example we're going to run 100 simulations. We set up the minimum maximum coordinates, and then we can go and set the various search conditions. So as we mentioned earlier, when we did our variography, we decided that we would set a 1500 meter search in direction 1 and a 1000 meter search in direction 2. So this simulation has been run already. It takes probably 20 minutes to run a simulation of this size. Yeah, over 100 simulations, realizations, and once it completes, we get this main view output, and this describes or shows us the mean and variance results for each domain. So here's domain 100, domain 200, and domain 300. The diagram shows box and whisker plots for the mean, the sample variance, and the idea is that the mean should be as close as possible to 0. So in domain 100 we have a mean of approximately 0.15 and a variance of approximately 1.05. So we're looking for the variance to be close to 1 and the mean to be close to 0. And this indicates the closeness of agreement between the simulated data set, in this case 100 realizations at each point, and the actual data set. All of these results here are perfectly acceptable and reasonable, but we can note that in domain 2 they are particularly good, with the average of the mean being very close to 0 and the variance very close to 1. So we will accept this run and go ahead and look at some of the output results. You'll notice in the project tree that we've now generated our simulation results for raw ash, and we've also reblocked these values to a series of increasing block sizes. So if we look at the simulation results and we expand the tree and we have a look at the E-type, which is the average of all the simulations, we can go and view this in the 3D viewer. So here we see the output of our 100 simulations across all of the domains, and we're looking at the distribution of ash values that have been simulated, colored according to deciles. So if you recall the data, we had some very high data points, ash values in this area here, and this is reproduced in the simulation. We also remember that the central domain 200 generally had higher values than the domain 100 and domain 300. So if we were to compare this to the sample results, we would see that this simulation has a pretty good representation of those simulation results. In our variography for domain 100, our principal direction was somewhere in that direction there, and you can see that coming through in the simulation. In domain 200, if you recall, the principal direction was something like that, and you can see that coming through again in the simulation. In domain 300, we ran essentially an omnidirectional variogram with no preferred direction. If we remember that the E-type is the average of all the simulations, we can then go and look at individual simulations that ran. So this is simulation 1, and if we just click through these, you'll see the picture changing, and you'll see the results of individual simulations that ran. And all of these results of each of the 100 simulations has been averaged into the E-type here, which is our overall estimate. For the 50 by 50 meter grid that was set up for the original simulation run, if we look at exactly the same information but now reblocked up to 500 by 500 meter size blocks, we can see the same overall pattern of distribution of ash, and then up to 1000 by 1000 meter blocks. The larger blocks can be useful for looking at volumes over particular production periods, for example, quarterly or annual periods. We can also look at QQ plots of this simulation. So, for example, here for domain 100, we're looking at a QQ plot that's plotting the simulated results against the sample results, and we can see an extremely good correlation between the two, up to an ash content of around about 30%. Above 30% ash, the simulation tends to overestimate the average grade of the blocks, but the overall result is very pleasing. Another very useful feature is to look at the probability above and below cutoff. So for each of the block sizes, we can look at the probability cutoffs. In this case, on the 50 by 50 meter blocks for ash content at a cutoff of 15%. So in the color legend down here, where 0 is dark blue and red is 1, this represents a color coding or color gradation between 0 and 1, or 0 and 100% probability that the ash is greater than 15% over our deposit. And so we can see that at a cutoff of 15% ash, the vast majority of the deposit will have ash contents above 15%, except for a small area here where the probability is around about 50% that it will be above 15%. We can also double click on this to expand these and have a look at them in more detail. And for each real life or cutoff value, we can see that in the case of 15% ash, the mean grade above cutoff is 19.74% ash, and the mean grade below cutoff is 14.5% ash. To get back to the original view, we just double click in the right hand corner. So at a cutoff grade of 20%, we can see that domain 200 is by and large will have an ash content greater than 20%, with its average grade above being about 22% and the average grade below about 17%. We're looking in this case at the ash variable, and we're probably more interested in low ash rather than high ash. So we would probably be interested here in the average grade below cutoff for ash. But you can easily imagine us doing a similar exercise for yield. So if we do the similar probability plots for yield above a certain cutoff yield, we can obtain some very useful information as to the probability of the deposit to produce above a particular yield and the associated financial implications that go with that. So these types of probability plots are a direct output from your simulation and can be very useful. Another very useful functionality within Supervisor is to export the results of your conditional simulation to a CSV file. And here we have the opportunity to export any of the results from any of our reblocked model simulations. In this case, we'll go with the 50 by 50. We can output the probability above cutoff, the mean grade above cutoff, and then all of these common statistics here. We can also output confidence intervals around our estimates. And there are a couple of hard-coded ones here, and here's the ability to customize your output, and in this case we've chosen what will be a 90% confidence interval, and then we just hit the export button. Here's an example of the output CSV file for the 50 by 50 meter blocks. So we have the coordinates, X and Y coordinates of each block. We have the results output per domain, and then we have the results of every simulation. In this case, we've run 100 simulations. Here's the E-type value, which is the average of all of these simulated values. So for this particular node in the 50 by 50 meter grid, we simulated a value of 24.5% ash. The variance and the standard deviation of the 100 simulations are recorded. And in this area here, we can see the probability above cutoff, so in this case 14% ash cutoff, and the average grade above cutoff. And that's repeated for all of the grade cutoffs that we specified. So in this example, we asked for confidence intervals at a 50% confidence level, in other words, the interquartile range. And we also asked for confidence intervals at a 90% confidence level. And here we can see the average ash content of 23.8% ash at a 90% confidence interval for this particular block. And the range of ash values from the 100 simulations ranged between 17.6 and 41.6% ash. The variance of the simulations within this range was 51. The mean percent means that the actual mean value is located at the 70th percentile, which implies that the population of these simulations is somewhat negatively skewed, as is borne out by the median at a 90% confidence interval. The median is 20.1, which is slightly less than the mean value. So this data represents all of your simulations and the relevant statistics that go along with it, available to you here in spreadsheet form. and available for any post-processing that you wish to carry out. A very useful statistic that we can calculate from this information is the coefficient of variance, or the CV, which is simply the standard deviation divided by the mean. And this gives us a value that we can compare block with block, and gives an indication of the precision or confidence of the estimate in a particular block compared to other blocks. And we are going to use this CV data output and load it into our Mindscape geological model and contoured there to give us some, to be able to compare blocks and obtain a view of the confidence in the estimate of those blocks compared to each other. And this data we will contour in Mindscape to help us with our resource classification. For the last part. Okay, so we're nearly at the end. So here's the output contoured loaded into Mindscape and contoured. In all cases, the coefficient of variation is very low compared to other mineral deposits. But at a 50 by 50 meter block scale, we can see that for less than 0.05, see coefficient of variation. These grayish areas here are illustrated for 50 by 50 meter blocks. So what we are able to do now is compare one block with another block, or the relevant confidence in its estimation with the relative confidence in another block's estimation. And we can see this for our deposit here for 50 by 50. If we look at the 500 by 500 meter blocks reblocked, the variation of the estimates goes down, and we can see now that the 0.05 or less than 0.05 COV covers a much larger area where the blocks are bigger. And 500 by 500 meter blocks may represent maybe your quarterly production, something like that, depends on your production rate. But this gives you an idea of the confidence in the estimates at different timescales and different block sizes. And we've used ash as a theme throughout this. We can use anything you like, any other variable you've loaded, and particularly useful for deposits that undergo washing is the yield to produce a particular product. So it's quite informative to do a similar exercise with yield. I just listed on the side here some references to papers that describe this sort of thing and give you more background information. You're welcome to go and look those up, and they'll give you references to a host of other data or papers if you're interested in this sort of thing. So that concludes my presentation for today, and I'm happy to take